radius is defined as the distance from the center of the nucleus to the outermost shell of an atom. Let's see what atomic radius actually is. Suppose this is an atom, here is the nucleus and this is the valence shell, and the distance between them, which is here, that is atomic radius. Now we'll find three types of different radius. Why? Because some elements form covalent bond. So for those elements we will find covalent radius. Elements which form metallic bond, we will find the metallic radius, and the elements which does not form any bond, we will find the van der Waals radius. So once again, different type of radius. Covalent radius for those type of elements which form covalent bonds. Van der Waals radius for those type of elements which does not form any kind of bond, and for metals we have the metallic radius, or we can say it is crystal radius, right? So starting with the covalent radius, it may be defined as the half of the distance between the two nuclei of covalently bonded atom, but the atom should be same, right? And bond should be the single bond. For example, in H2Cl2Br2I2P4S8 and diamond, they all form the single bond. Therefore, we will find the covalent radius of these type of elements, right? So how to find the covalent radius of the element? Just look at this. This is a molecule. A covalently bonded atoms are there. This is one atom, this is another atom, and this is molecule. Now what we are going to do, we are drawing the lines from the nucleus of the atom. So these are the lines which are passing through the nuclei of the atom. Now this is called internuclear distance. So this is internuclear distance, means the distance between two nuclei. Now what we have to do, we have to take half of it, and its half of it will be this, and this distance is called covalent radius, right? So this was the covalent radius. Now let's discuss about the van der Waals radius. Now according to the definition, the van der Waals radius is the half of the internuclear distance of two neighboring molecules, and the atoms should be the closest one, right? And this van der Waals radius we use to find out the size of those elements which does not form any bond. For example, the noble gases helium, neon, argon, krypton, etc. Now what is this van der Waals radius actually? Now for example, this is a molecule and there are two lines passing through the center of the molecule, that is from the nuclei of the molecule. There is another molecule and there are two more lines passing through the nuclei of the molecule, and this distance in the internuclear distance, and you can clearly see this molecule and this molecule both are neighboring molecules. So as per the definition, the molecule should be neighboring. So this molecule and this molecule both are neighboring molecules, and this atom and this atom are the closest atom. So what we will do, we will find out the half of this internuclear distance, and to find the half of the internuclear distance we have to draw a bisector. So this is a bisector and this distance is van der Waals radius. And one more thing I want to tell you, if we find out the covalent radius of this molecule, the second one, the covalent radius will be this, and we can say that in general the van der Waals radius will be always bigger than the covalent radius, or the covalent radius will be shorter than the van der Waals radius, right? Now let's move on to the third one, that is metallic radius. That is for metals, and that is explained like it is the half of the distance between the two adjacent metal atoms, and the metal atoms will be something like this. This is one metal atom, this is another metal atom. So what we have to do? We have to first draw a line through the nuclei of these atoms. So this is the line from the nucleus of the atom, and this is where the atoms are touching each other. Now, this distance is the metallic radius. So guys, we find the different type of radius for the different type of elements. Elements exist in three ways. First, they will either form the covalent bond. So for those type of elements, we will find the covalent radius, or they will form a metallic bond. For these type of elements, we will find the metallic radius. And if the element is not finding any kind of bond, we will find the van der Waals radius, as we do it for the noble gases. So, moving ahead, in periodic table, if we go down the group, the atomic radius increases. Why is it so? It is because the number of shells increases. And while we go across the period, so when we go across the period, atomic number also increases. It means that number of protons are increases in the nucleus, and number of electrons are also increasing in the shell. So what will happen? You are increasing the positive charge also, you are increasing the negative charge also. So there will be more attraction and the size will decrease. Let's discuss in detail. Now, for example, if we take the first group, the first element is lithium. You all know that the electronic configuration of lithium is 2,1, and the atomic radius will be this. If we take sodium, sodium will be 281. There is an extra shell in sodium. So the atomic radius of sodium will be bigger than that of lithium. So you can clearly see that the radius of the sodium is bigger than that of lithium. If we talk about potassium, so now we have 4 shells. The electronic configuration is 2881, right? And if you find out the radius, radius is the distance between the nucleus and the valence shell electron. So this will be the distance, and from this diagram you can clearly see that potassium will have bigger radius than the sodium, and sodium will have the bigger radius than lithium. That's why down the group the radius will increase, right? So let's move on to the period. What happens in across the period? Now you know that the formula of the electrostatic force is F is equal to K Q1 into Q2 upon R square. It means that electrostatic force depends on the product of the charges. So what we are going to do across the period? Here you can see that there is a continuous decrease in the size. Why is it so? Because the nuclear charge, means the charge of the nucleus of lithium is +3, and the total number of electron is also 3. So it will be 3 into 3, that is 9. So you can understand, I am not taking the charge of electron, that is 1.6 into 10 to the minus 19 coulomb, but I am taking just unit charges. So positive 3 unit charge is present on the nucleus of the lithium, and minus 3 charge is present on the total electrons of the lithium. And in the case of beryllium, the nuclear charge is +4 and the total number of electron is 4, that is charge is -4. So 4 into 4 is 16, and 16 is bigger than 9. We all know this. And if you go to boron, again the nuclear charge is increasing and the number of electrons are also increasing. Again in the carbon it is +6, that is -6. In the nitrogen it is +7 and -7. So it will keep on decreasing as you are increasing the charge in the nucleus as well as in the shell. So positive charge is increasing in the nucleus and the negative charge is increasing in the shells, right? So let's move ahead. Let's discuss about some exceptions. Now guys, we all know that the radius of the atom keep on decreasing across the period. And if it is so, then the radius of the noble gas should be the least. But it is not true in all the cases. Why? If we consider lithium and neon, the second period, right? So if we find the radius of neon, we will find the van der Waals radius of neon. And since lithium is a metal, we will find the metallic radius of lithium. So if we compare the value, in that case, the radius of neon is bigger than that of lithium. And similarly, in third period, argon is bigger than that of sodium. So what is ionic radii? According to the definition, the ionic radius is defined as the effective distance from the nucleus of the ion to point up to which it has an influence in the ionic bond. What is the meaning of influence here? The meaning of influence is the attraction. If cations and anion are separate, then we can't find out the radius. They should be in the influence of each other like this. So this is cation, that is anion. If you draw a line through the nucleus of the cation and a line where the cation and anion are touching, the distance between this middle line and the line passing through the nucleus of the cation will be the radius of cation. And if we draw another line passing through the nucleus of the anion, the distance between the middle line and the line which is passing through the nucleus of the anion will be the radius of anion. So that's how we find the radius of cation and anion. And you know one thing, the radius of cation will be always smaller than the parent atom. For example, if you find out the radius of sodium, that will be bigger than Na plus. And if we find out the radius of chloride or chlorine, chlorine will be smaller than that of chloride, right? So this was all about the atomic and the ionic radius. Now, first we have to know that what is the meaning of ionization energy. Ionization energy is the energy, the minimum energy required to eject the electron from the valence shell of the isolated gaseous atom. Now, here again the question arises, what is the meaning of gaseous atom? Why we are taking gaseous atom? Why not liquid? Why not solid? If the atom is bonded to the other atom, definitely the nucleus of other atom will influence the electron of the valence shell. And we don't want that. We only want that the nucleus of that atom should attract the valence shell electron, not the nucleus of other atom. That's why we always take isolated gaseous atom, right? Now, if there is an atom that is A, or there is element A, it gives A++ electron and delta H is x kilojoule per mole. And what is delta H? Delta H is the enthalpy change in this reaction. Now, delta H is enthalpy. Enthalpy we will discuss in thermodynamics. For now, for this chapter, for you, enthalpy is the energy required. So the energy required for this process means to convert this element A, which is in the gaseous state, to the gaseous ion, x kilojoule energy is required for 1 mole. So this is the ionization energy. Now, we have to know what are the factors affecting ionization energy. First is the size of the atom. Now, if the size of the atom is big, the valence electron will be far away from the nucleus, and it is very easy to eject the electron from the valence shell, right? And if the size is small, then it will be close to the nucleus and the ionization energy will automatically increase because the nucleus will attract effectively that valence shell electron. That's why we can say that as the size of the atom increases, ionization energy decreases because the valence shell electron will go far away from the nucleus, right? So, moving on to the second point is the nuclear charge. Higher is the nuclear charge, better will be the attraction, right? So, if we are increasing the nuclear charge or the atomic number is increasing, the ionization energy will be more. Therefore, as the nuclear charge increases, the ionization energy also increases. The third point is screening effect. Now, I know that this term is new to you. The screening effect, or we can say that it is shielding effect. As the shielding effect increases, the ionization energy decreases. But what is shielding effect? Let's discuss about shielding effect. Now, this is lithium. Electronic configuration of lithium is 2, 1. Valence electron, 1. Now we want to eject out this electron, right? So, there are two factors. First is, nucleus is attracting this valence electron. It is increasing the ionization energy. Second thing is, these two electrons which are moving in the K shell are coming in between the nucleus and the valence electron. And what they are doing? They are shielding that valence electron from the nucleus. So how many electrons are shielding? There are 2 electrons which are shielding, which are decreasing the effectiveness of the attraction of the nucleus on the valence shell electron. There are only 2 electrons. But in the case of sodium, there are 10 electrons. You can see that the electronic configuration of sodium is 281, and we want to eject out the electron from the M shell. So, there is K shell having 2 electrons, there is L shell having 8 electrons, and what the electrons will do? These electrons will come in between this valence shell and decrease the effectiveness of the attraction of the nucleus on the valence electron. This is called shielding effect. And if this shielding effect increases, then the effectiveness of the attraction of the nucleus decreases. And if it is decreasing, then ionization energy will be definitely very low, right? Let's move to the other point. The next point is penetration. Penetration means the closeness to the nucleus. Closer the electron to the nucleus, more will be the ionization energy. Because if electron is very close to the nucleus, nucleus will attract it more effectively. Let's take an example. Again, we are taking the example of lithium. Now, these 2 electrons which are present in K shell are near to the nucleus, and this electron which is present in the L shell is far away from the nucleus. Or we can say that in first shell there are 2 electrons which are more penetrated. In the second shell there is 1 electron only, this is less penetrated, and we can easily remove this electron. But if we want to remove these electrons, they are more penetrated, they are highly attracted by the nucleus. That's why it is very, very difficult to eject out these 2 electrons. So this was penetration effect.